All right, so now what I want to do in this video is I want to give a way to numerically compute the derivative of a function using the difference quotient. Okay, so that's what I want to do. And again, since we don't know how to write functions or anything like that, some of this stuff is going to be hard coded that we might not want to have hard coded. But let's say our goal in for this video, our goal is to compute the derivative of the function y is equal to x squared plus x plus 1. Like, this is what we want to compute the derivative of. Okay, just making sure. Using the difference quotient. Okay, so an approximation is, and we could do, an approximation is, well, I'm just going to do the difference quotient. I'm going to call it dq for difference quotient. Difference quotient, this should like go on its own line. Difference quotient, this is LaTeX, and we'll get to LaTeX later in this class. Should be x, so a plus h. So a is going to be the point at which we're computing it. A plus h squared plus a plus h plus 1. And then we're going to do minus a squared plus a plus 1. Okay, and so notice h is going to be positive. Well, in my mind, it's positive, and in the code we will write, it will be positive. So this is kind of really just computing the right-hand derivative. If the function is differentiable, the right-hand derivative is equal to the left-hand derivative. And I don't really want to talk too much about like whether this is the best numerical method. So let me just make this look nice. Okay, so this is what we want to compute. Now, if we're going to start off by computing this. The code, we're just going to have h is equal to like 1/2, and this should be a good approximation to the derivative. And then we're going to make h get smaller and smaller and smaller, and then see a way to kind of automate the smaller and smaller and smaller. Okay, so now we're going to say a will be equal to, we'll say a is equal to 1. I mean, we'll be able to change a, but for now, let's say a is equal to 1. Let's start off with h is equal to 1/2. I'm going to write this as 0.5. And then the difference quotient. The difference quotient is just going to be like this, but in Python. So a plus h squared. Whoops. Hey, a plus h squared plus a plus h plus 1, and then minus. Make sure you do parentheses to put that whole thing in there. A squared plus a plus 1. Okay, if you want, you can go ahead and simplify and cancel out those ones. I'm just going to leave it like this for now. This, and we're going to divide by h. And then we want to print dq. Or let's say we'll do this. The derivative is approximately equal to, okay, and everything, okay, so think about what this should be. Okay, so the derivative of this function evaluated when x is equal to 1, we should be getting 3. Let's see how close this is going to get us to 3. Okay, 3.5, not a bad approximation, but not, we know it's not very good. So let's see what happens if we half h and we run this. Approximately 3.25. Okay, let's see what happens if we just go down to let's say 0.1, and let's run this. Or let's go back, actually, let's do 0.25 divided by 2. Let's run this code. Okay, 3.125. What about 0.25 divided by 4? Let's run this code. Okay, we're getting better. Okay, let's just jump it up to 64, and let's see what we get when you run this code. Okay, got some good accuracy here. It doesn't have to be, we don't have to divide by powers of 2, but that's what we're going to see in the code, so that's what I'm doing here. Okay, even better, and so on and so forth. And we can see how this would increase. Or we could do something like this, 2. Now I can make this, so, all right. All right, and so on and so forth. You can see how this would go. Okay, so now let's try to write code that's going to do this automatically. That's going to keep computing difference quotients with smaller and smaller values of h, so that so that we have the answer within a certain tolerance. Okay, now one thing that we have to think about when doing this, we know the answer here is 3. Like, we know that the answer is 3 because we can compute the derivative and plug it in. But let's say we don't know that what the derivative is supposed to be, which is one of the applications. We want the computer to compute the derivative for us. It doesn't know what the derivative is, so we have to tell it when to stop computing. So we're going to have a tolerance. So let me just, sorry, let me, okay, so what we want to do, if you know what a Cauchy, like if you know what a Cauchy sequence is, we're going to use the following fact: if a sequence converges, then it's Cauchy. So what we really want to do is we want to compute difference quotients with smaller and smaller h values until our answer is within a certain tolerance of the actual derivative. And if the function is differentiable at a point, we know that that's eventually going to happen. However, we're going to use the fact that if a sequence converges, it's Cauchy, meaning one of the things it means is that successive terms get smaller and smaller and smaller. So what we're going to do is we're going to keep computing the difference quotient. We're going to keep getting smaller and smaller values of h, like until two successive difference quotients are really close to each other. Because if they're really close to each other, then they're probably close to the limit as well. Okay, so I'm going to introduce a new variable. I'm going to put h here back to 0.5. I'm going to introduce a new variable here called tolerance. That's how close successive approximations are going to be. This is going to be equal to 0.1. And we're going to start off our difference quotient as being this. This is going to be our initial difference quotient. And now we're going to do a new sort of thing that we haven't talked about yet, but it's similar to if. It's called while. So I'm going to put while, and I'm going to introduce a new variable called delta. Delta will be the difference between the two difference quotients. So delta are successive difference quotients. So I'm going to put delta as 1 now. So while delta is greater than tolerance. So delta is going to be our distance between successive approximations. And by the way, it's probably good with this one specifically, but also with other ones as well, to sort of pause what I'm saying and ask yourself if what I'm saying makes sense, and kind of think about what I'm doing here. So while delta is greater than tolerance, that is, delta is going to be the difference between two successive approximations. So while delta is greater than my tolerance, I want to make I want to divide h by 2. So I want to say h is h over 2. If we want, we can write divide equal to like that, like we did with plus equals, but I'm just going to say h is equal to h over 2, or 0.5 times h. Okay, so h is equal to 0.5 times h. I'm going to compute a new difference quotient. I'm going to call it dqu for dq updated. It's going to be the same formula here, but I have a new value of h because I halved h. So that's what dq is. Delta is going to be equal to, I'm going to write mp for numpy. So remember, if you're running this, so actually, let me just do good coding practices. Import numpy is in p. There's other ways to get absolute value, but I'm going to use numpy. Absolute value of dqu minus dq. So this is the difference between my successive approximations. Okay, delta is equal to np, the absolute value of dqu minus dq. Okay, but now I need to now set dq to be equal to dq, the updated version of dq. Okay, so I'm just replacing variables. So like dq is equal to 3.05, dqu is something equal to a little closer to 3, and now my old dq is equal to dq updated. And if delta is greater than tolerance, in other words, if my successive approximations are still far enough apart, I'm going to do this whole thing over again. Okay, so now delta is equal to 1, a is equal to 1, h is equal to 0.5. Everything seems okay. I'm just going to make tolerance equal to, I'm going to make delta 2 and tolerance equal to 1. So we're not going to run through this loop very many times, probably not even once. So let's go through this. Okay, so the derivative approximation is 3.25. Okay, so now let's say I want my tolerance to be 0.01. Now I'm going to run the code again, 0.01, I'm going to run the code again, and I'm going to get something that's closer to 3.25. And I do. And if I do blah, 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 make the tolerance very, very small, and run the code, I'm going to get something, I get exactly 3 here, to the precision of whatever I've given. Okay, let's compute the derivative when x is equal to 0, or when a is equal to 0. When a is equal to 0, the derivative should be equal to 1, so let's see if this works. Okay, 1.0. Let's do one more. Let's do the derivative when a is equal to 2. Let's do when a is equal to minus 2. So the derivative is 2x plus 1. So 2 times minus 2 is minus 4. So the answer here should be minus 3. And it is. Okay, so that's it for this video. There is a lot contained in this video. Think about what this video is doing. And try to come up with a problem like this and code it yourself. Maybe instead of taking the right-hand limit, you take the left-hand limit. Or you can do the symmetric limit where it's like a plus h, f of a plus h minus f of a minus h over 2h. Try to code something like that. There'll be a question like that on the homework. That's it for the videos that I want to make this week. I will be posting a homework assignment either today, Wednesday, or tomorrow, Thursday. Probably it'll be Thursday. And you're going to be doing things like this. All right.